move on and actually get started. Okay. So like I said, this is an introduction to neural networks. So what is a neural network? So for a simple analogy, neural networks are like our brains. There are nodes and there are connections between them. Each node is a part of a layer of nodes. In the neural network depicted in the image, there's an input layer, which are basically the data features which we put into the model. And those are connected to two hidden layers. So what are these hidden layers actually doing? So these hidden layers, their main purpose is making connections between the input layer and the output layer. So they're basically like the intermediary layers. And the goal of this whole network is to accurately predict the output using the input. And so the hidden layers are just in the middle and trying to make the best possible connection between the inputs so that they can get the correct output. And of course, the hidden layers are so much more intricate and complex, and you can make it as complex as you want it to be. So now you might be wondering, now you know the architecture, so how does the model actually learn? It is called machine learning for a reason. So to answer this question, we have to look at the neural network as one big entity, like all the connections, everything as one solid block. Okay, if we do that, now we can understand that the network is repeated countless times. And each time the model keeps track of its accuracy, how well it's doing against the data. So this is where the concept of weights and biases are introduced. So every time the model iterates, it tweaks its weights and biases, which basically helps control the signal between two neurons. In this example, the weights and biases are inside the hidden layers. And these values are tweaked in every iteration. And through trial and error, the model learns the connection between the input and output with the correct data, of course. Okay. So now it's important to note that a neural network is useless unless there is data. A really good resources for finding data sets is calc.com. And I'm pretty sure you guys might have come across it. So let me just type in how you can get to the website in the chat, and that's the URL. I'll be using the data set from Kaggle in this workshop. And there are so many data sets to choose from. There are literally thousands, hundreds of thousands of data sets. And so what I recommend doing, trying to filter those to trying to pick which one I should use, what I usually do is I search machine learning. And then after that, I type whatever topic I want the data set to be, like something about cars, something about airplanes, something about biology, or anything else. And if you use those to filter, you'll be able to narrow it down to a few thousand results. And the most popular ones will always show up first, so you can choose those. Okay, so the data set which we'll be using in this workshop is a star types data set. So this data set describes the characteristics of over 200 stars, and it categorizes them through values such as luminosity, color, magnitude, and spectral class, and many more. This picture is actually taken from the Kaggle dataset website, and it was uploaded by the person who also uploaded the dataset, and it plots the different stars that could exist in the dataset. So it ranges from like supergiants like Betelgeuse to main sequence stars like our own sun, and to smaller white dwarf stars like Sirius B, and so on and so forth. So in this workshop, we're going to be using a star's luminosity, magnitude, color, spectral class, and other characteristics to try to predict whether it's a supergiant, giant, subgiant, main sequence, brown, or white dwarf. So that's basically the goal of this workshop. Okay, so now let's actually get into some coding. So this is going to be an interactive session. So let me just open my Google Colab here. Okay, let me share another tab. This one. Okay, empty Colab notebook. So we're going to be using Google Collaboratory for this. So please open up a Google Colab so you can code along with me. And you don't have to worry about copying the comments. Those are just some pointers that you should, those just describing what I'm going to type in those boxes. So so please open up Google Colab. It's free. You can open it with your Google account. And when you open Colab, you can create a new notebook. And this is what you'll get. Every time you want to add a new code block, you just press this add code button, and then it'll add a code block. So, okay, please let me know if I'm going too fast. Yeah, exactly. Thanks, Sanjeev, for sending the link to the Colab. Okay, and please let me know if I'm going too fast so that you guys have enough time to open up the Colab and get ready to start coding. Okay. So first off, we're going to import some Python libraries, which we'll need, some basic ones. You'll probably use this for every machine learning project you'll do. So first we will import NumPy as NP. You can name it. I just chose NP because it's like the acronym for NumPy. So you can choose anything. It's just NP is what I'll be calling it throughout the whole program. So you can name it whatever you want it to be called by in the program. So okay, NumPy is 1, and then you can import pandas as PD. So NumPy is basically the math library, and pandas is a basic data science library. So it'll provide the functionality to import data, to read it, and to edit it. So, okay. So I hope everybody was able to get those libraries imported. And just to be safe, we'll just run it and see if it produces any errors. This run button, this play button right here. Okay, so no errors showed up, so we can now move on. Okay, so now let me provide the dataset link so you guys can go ahead and download it. It's a Kaggle URL. Make sure you click on it and then download the dataset. If it asks you to create a login, just quickly create a login, use your Google account. If you have like a spam email, then use that spam email, because I always get emails from Kaggle for random stuff. So yeah, you can always unsubscribe to their emails. So just quickly download the data set, and then I'll show you guys how to upload it to Google Colab. If you have any trouble downloading the data, please let me know in the chat so I can help you guys if needed. Okay, looks like there's no problems downloading the dataset. Okay, so I'm not sure if you only download it. Yeah, you can actually, yeah, good question, Zane. You should actually unzip it and get the CSV file ready to be dragged into Colab. So just unzip it. Yeah. And you can rename the CSV file to whatever you want. I generally name it like 1 or 2 words separated by underscores so that I can easily import it. If it's like a really long name, then it's really hard to import. I have to type out the whole file name. So name it to whatever you want. I named it star data. I'm not sure if it came like that or that's how, or I just renamed it like that. But you can rename it to what I named it so that we can be consistent. Okay, so once you've got the CSV file, you can drag it into this this folder section. So there's like a little folder icon in the middle left of the Colab. You can click that, and it should open up this couple of files, sample data, and then this Google Drive upload thing. So you can just drag it and place it here, and it'll automatically upload to Colab. And make sure you save this data file locally also in a safe place, not just in your downloads folder or something else. Make sure you save it in a place where it won't be deleted or accidentally modified. Okay, so now if it's successfully uploaded, you will see stardata.csv. and it should just be there. Is everybody good on that? If everybody's good, we can move on. Yeah, 6class.csv. You can either leave it like that or rename it to what I have. Yeah, exactly. Like Willie just said, extract the file and then get the CSV and then upload it to Google Colab. Yeah, 6class.csv is what it is when you download it. You can rename it or keep it like that, but make sure you drag it into the Colab. Okay. Okay, looks like we're all good there. So now we can actually go ahead and import this data into our code. And for that, we can do data equals PD, which is our pandas library. And then there's a function in that called read CSV, read underscore CSV. And in parentheses, we're going to put the name of the file. So for me, it's stardata.csv. If you kept the name the same as you downloaded it, you have to type in 6class.csv in the same, lowercase or uppercase, and however the case is. Make sure you copy it exactly. Copy it exactly, and then press enter, and then we go to the next line, and you can do data.head. So what this .head function does is it basically prints out the first 5 rows of the data set. So if we go ahead and run this block of code, you can see we get the first 5 rows of the data set. Was everybody able to put these 2 lines of code there and print out the first 5 rows? Nice. Cool. Awesome. So now you can talk a little bit about the data itself, now that we can see it. Okay, so there are 7 columns or features, which I'm going to be, like how I'm going to be referring to them throughout this workshop. There are 7 features or columns in this data set, and there are 240 rows of information. Okay, and there are 240 rows. Yeah. Okay, now that we look at the data, we can now determine what is going to be your input to the model and what is going to be your output to the model. So we're going to use this data, the input from this data, to predict what kind of star type it is. So basically, right off the bat, we can obviously know that the star type is what we're trying to predict. This column right here, star type. And the other 6 rows are going to be your input to the model. Okay, so 6 rows for the input, 1 row for the output. Okay, so a little bit more about the type of model we're going to use. We're going to be using a supervised learning model, which basically means that the data we're feeding into the model is going to be labeled. So like obviously that you can see that the columns are labeled. The model actually knows which column is what, which values are in which column. So that's what supervised learning model does. It knows that the data is labeled and which column it belongs to. Yeah, and therefore it can know where it went wrong and try to predict the star type the correct way. And okay, so that's our data all taken care of. Now we know a little bit about the data. And at this point, it's very tempting to just throw this data into a neural network by just looking at a tutorial and then just calling it a day. But there are some important steps we need to take before we can actually put it into the neural network. And this is called pre-processing. Okay, so we can get to know a little bit more about our data by doing data.describe. It's basically describes the data, doing some basic statistical analysis. It says count how many rows are there. So this is where I got the 240 from. This is how many rows there are. And this is the mean. Obviously, for each column, there's a mean and standard deviation, minimum, maximum, all those things. So you can kind of know how the data is structured, like how big are the values, how small are the values, what is the standard deviation, how far apart are the values from each other. So you can know all that. But I guess the most important thing is knowing how many rows are there, because you want to know how much you're inputting to the model. Okay, so that's just a quick little function. We can now press the X button to take out that, since we're going to be coding some other stuff. Okay, now let's move on. Okay, so there are many things you can do. Like I was talking about pre-processing, specifically, you can do a lot of things that can clean up your data. So here are just a few examples. Like the comment says, we're going to check for null values, which means that we're going to look for incomplete data, because we do not want to give incomplete data to the model, because it'll either spit out an error or it'll falsely train the model, both of which is not the goal of this workshop. So how do we check for null values? So we do data dot is null dot sum. Okay, now let me explain. Is null is pretty self-explanatory. It's going to check if there are any null values in data, which is where our data is. And dot sum is what dot sum is going to do is it's going to sum up all the times it sees null values and then print out an integer. So if it prints out 0, that means there are 0 null values. If it prints out 10, that means there are 10 null values. Okay, so now we can go ahead and run this. And thankfully, this data was super clean, and there are no null values in any of the columns. And as a bonus, the last thing it shows is dtype, which is basically data type. It'll show what data type each column consists of. And in this case, it's like N64 for all of them. Okay, so that's good. Now we check for null values. That was a good pre-processing step. Okay, next we check if there are columns or features which are irrelevant to the output we're trying to predict. So we have to think, is there any column that's not necessary to try to predict the star type? And if we check back to the first 5 rows that we printed, and if we look at the columns, there doesn't seem to be any unnecessary columns in this. So all of these are important factors in trying to predict the star type, because these are defining characteristics of stars. Like throughout the astronomy field, these are super important things which help classify stars. So if there were unnecessary columns, what you would do is you just do a simple function called data.drop and then parentheses, and then you would put all the columns which you think are not necessary. So let's say temperature was not a necessary column. So you do data.drop, parentheses, and then brackets, and then the column name. And then what that would do is you can say data equals data.drop, and it would store all the columns except temperature in the data. So it basically removes it and returns the rest of the columns. So that's a pretty easy, handy function to help eliminate any columns which are not necessary. Okay, so we checked if there are no values, and we also checked if there are columns which are not necessary, both of which we can now move on from. And finally, it's vital for any data to be normalized or standardized. Okay, let me quickly switch to these slides. Okay. Bear with me, please, as I switch tabs to my explaining the process of standardization and normalization. Okay. So hopefully this this picture of the star distribution makes more sense now, since we now looked at the data. Okay. Anyway, moving on for pre-processing the data. Okay. So we did the first 2 bullet points, and now we're talking about standardizing. Okay. So what does standardizing or normalizing mean? So first we'll talk about normalizing. So normalizing the data basically means to simplify the data between 2 numbers. For example, if you have a bunch of NBA players and you want to normalize their heights, since they're like a wide variety of heights in the NBA, you can normalize those heights from a decimal between 0 and 1. Okay, so One person's normalized height would be 0.2, another person's would be 0.7. Okay, so it's all between decimals. It's all decimals between 0 and 1. Okay, and data normalization is beneficial because it increases the cohesion of the data by basically scaling it to a certain range. So if the model knows it's between a specific range, then it can better make use of the data and it'll make sense of the data better. But in my case, I chose to do data standardization. And as you can see, the quick formula on the slides, it's called z-score standardization, which is slightly different than normal standardization. So instead of confining the data to a range, what z-score standardization does is it makes the widely distributed numbers of the data set more uniform. It doesn't restrict it to 0 and 1, but it can be, there's no, there's not a specific range. It can be starting from -2 all the way to like 20, but it makes it more uniform. And it's more easier for the model to systematically make sense of the data. Okay, and it's calculated through taking the data points and then subtracting the mean of the whole data set and then dividing it by the standard deviation. Okay. Okay, let's see if there are any questions. Okay, like we had a question about, okay, Sanjeev's taking care of that. Thanks, Sanjeev. Okay. Okay, now that we know a little bit about standardization, we can go ahead and start actually coding the standardization. Let me just quickly change my screen sharing thing. Let me make it so that I can share a window instead of a specific tab. Okay. Okay, now you can see. Okay, so now what we're going to do is we're going to do the standardization. Okay, z-score standardization. And this is, here's a good link to, if you want to learn more about the math behind z-score standardization. Let me put it in the chat. It's a quick article. Okay. Now that we got that out of the way, now we can go ahead and do the z-score standardization. So what you need to do is you need to take data and then choose which column you're going to do it on. Now, if it's like in my case, you'll get a drop-down list of all the column names. If you do not, you would have to manually input these column names. So let me choose, so we need to standardize the temperature column. We need to standardize the luminosity. We need to standardize the radius. And we also need to do absolute magnitude. Okay, the star type is already in a range between 0 and 6, I believe, or 0 and 5. So we don't need to touch that. And the star color and spectral class, we have to do something different with them since they're actually not numerical yet. Okay, so we take these 4 columns and we standardize them. So how we do that is you do data and then in brackets, temperature, and make sure you copy the exact column name with the spaces and all these intricate details exactly. So, and then you do data, column again, temperature, and subtract data, temperature, dot mean. So there's a quick function that gets the mean of the data. And then you put everything that we just did in parentheses, starting from data, temperature, and all the way to dot mean. So put that in brackets. And then you do divided by data, brackets, temperature, dot std. And the function, so the function that calculates the standard deviation. So that's pretty handy. We don't need to do it by hand or by manually. And then we put all of this in another bracket. And then we do dot as type float 32. I think when I was coding this, it gave me an error since I didn't convert it to float. So just experiment yourself in your own project. If you need to convert it to float, you should do that like I did here. If not, you can just take out that part. Okay, so now if we compile that, let's hope that we get no errors. Okay, you get no errors. Make sure to run your code every so often so that you can check if you have any errors. So is everybody good with this? Were they able to do standardization on at least one column? Please give a thumbs up if you're ready to move on with the other columns. Okay, no problem, Jonathan. Let me know if you... Okay. Okay, so I hope you guys are good now with the standardization. The first line is always the hardest. From now on, we can just copy and paste the line and just change the column name, since everything we're doing is the same. The formula is the same, it's just the column is different. Okay, so I'll go ahead and move on with the same thing. I'll leave this code right here so you can write it down, copy it if you need. Okay, so now we're going to paste this 3 more times. There are 3 more columns which need to be fixed. And for this, we can do, what was the second column? Luminosity. This time there's no space. You have to make sure you watch out for spaces. This one doesn't have a space. Like luminosity L/LO without spaces. And we just copy it and paste it into the other places where it needs to go. Okay. Next is radius R/RO. Okay, and we copy this, paste it. Okay, let me do the rest, and then I'll leave you guys some time to finish it on your end. And then absolute magnitude. Magnitude is lowercase, so watch out for that. And then it's MV, capital M, lowercase v. Oh, and I forgot. Yeah, that's right. Absolute magnitude MV. Then paste it into the other slots. Okay. Let me just run this to see if I got anything error. Okay, no errors on this. Make sure you're able to run it without any errors. If you do run into errors, please put it in the chat. Okay, if we receive a few thumbs up or okay to move on signals, then we can go ahead and move on. Jonathan, Zane, are you guys good? Okay. Yeah, not much is supposed to happen because we haven't actually printed anything out yet. So after we print it out, you guys can check whether it's produced any error or not. Okay. Yeah, that's a good point. We can go ahead and print data.head, which is now going to show the normalized data. Okay, and this is how the output should look like. The columns, everything should stay intact, except the numbers inside the column should be slightly different. it's important that you get this output. Was everybody able to get this output? So Sanjeev, it doesn't shrink it to a range. It just it doesn't shrink it to a range. It just you got the output. Good. Okay. So it doesn't do it to a range. It just does it. There's no way to know what range it actually goes to. It just makes it more evenly spaced out, if that makes sense. Like the data points are, it's better spread out. Like if we were to not standardize it, there will be some outliers. There will be some data points which are vastly different from the others. So basically, this standardizes it and makes it all within equal spacing of each other, if that makes sense. Yeah. Yeah. And normalization is a lot easier than standardization. So I'm taking the hard route here, but it's a good learning point to know some also like stats. Statistical analysis or standardization is also good to know. Okay, so now we can move on. Okay. Okay, and then now we said star color and spectral class. Those are columns which we still need to convert to numerical data, since you can't actually, it's pretty hard to give string data to the model. So what we're going to do is we're going to do a simple replace method for this data. And I'm actually going to post this in the chat because it's really long, and I'll explain why it's so long. So let me paste it in the chat and just paste it into your code like this. Let me also paste it right here. Okay, so just one huge line. This is for the star color column. It replaces all the colors like red, blue, yellow with numbers, numbers between 0 and 10, because there are 11 colors. Okay. Yeah, and this is where the data really is not clean, because as you can see, this blue, some values are blue, but then some values are blue with a space, which is really hard to deal with. So I would literally manually look at what different variations of colors are there, like blue with a space, blue without a space, blue white with a capital W, blue white without it with a lowercase w. So those are all different variations, and luckily there weren't too many, so I could do it by hand. If not, I would probably opt for regular expressions if this weren't the case. If there are any more, if the data was much more diverse or different, but this pretty much worked for this. Yeah, and there's also one more line which I would like to send in the chat, another replace method, and this is for the spectral class column. So this replaces values like O and A and F to values between 1 and 7. This can be any number. I just chose 1 to 7 and then 0 to 11 for the previous one. Yeah, it can be any number as long as it's consistent. Okay, and now we can do data.head. We print out, we can go ahead and comment out the previous data.head so it doesn't print it twice. And if we run this, hopefully we'll get star color and spectral class are converted to numerical values. Okay, so this is another checkpoint if everybody's good. So I think in place is there because sometimes when you replace some things, it kind of moves it to the top of the data. So we don't want it to move it to the top every time it replaces it. So it replaces it in its own column and doesn't move it replaces it in its own row and keeps it in that row. So we don't want to shift values up and down. We just want to replace it in that row. So that's what in place does. It keeps it in place while it's being replaced. Okay. And these will be obviously different for different data that you use. This is just one example. not too much work, but not like no work for pre-processing the data. Yeah. Okay. Just for time's sake, we have to move on. You're good. Okay, thanks, Jonathan. So just for time's sake, we have to move on. And now we're gonna talk about actually preparing the data for the model. Okay, so before diving into the model itself, we first have to modify our data a little bit. So just bear with me. So I'm going to split the data frame, which is the data, into two smaller data frames. Okay, I'm going to split the original data into 90% and 10% chunks. So first, we're going to create a variable called data model, and we're going to say equals data dot sample f fraction frac equals 0.9. So this basically saves 90%, a random 90% of the data into data model, which is what's going to go into the model. And this is going to be another variable after this, data underscore predict equals data dot drop. I'll explain it after I write this line, dot model dot index. Okay, so what this model does is it takes data model, which is what we just did, the 90% of the data in there, and it drops everything that's in data model. So basically, it takes the other 10% and puts it in this variable. Just like I said previously, the drop function, it drops whatever's in the parentheses, but then returns everything except what is in the parentheses, if that makes sense. So it returns everything that is not in the previous variable, which is exactly what we want, because we want to split 90%, and then the rest goes to another variable. So 10% goes to data predict. Okay, so we have model data and prediction data. Okay, so now we have to split each of these into x and y's, x being the input and y being the output. So we're going to do data. We're going to first deal with the predict x. So the x is going to be, we're going to do data predict drop, and we're going to put the column which we want to drop, star type, and then comma 1. And we're going to enclose it in np.array. Okay, so the x is the input. So we want to drop star type and put everything else in this variable as an array. Okay, let me check if there are any questions. Oh, Sanjeev, for your answer to your question. One reason is because there's a lot of variations. Like I said, blue is with a capital B with a space after it, all those variations. We're just trying to normalize that. Another reason is I ran into a lot of trouble passing in words to the model. So this is just another way to simplify it. Okay, so now we have data predict x. Now we want to do the same thing with data predict y. So data predict y equals, again, we're going to do data predict, which is what we're pulling from. And then we want to pull only the star type column. Since this is our output, we want only this column to be stored in the y. And then we obviously put np.array before it and put parentheses around it. So this is our data predict x and data predict y. This will make more sense once we do the splitting x and y for the data model variable. This is for the data predict. So hopefully if you run this, it'll not produce any errors. It would obviously not print anything because we're not printed anything. Okay, so now we have to split the data model into x and y, and this is where it's a lot more easier. So we do import sklearn. Scikit-learn is it's basically a machine learning library which helps split it into training and testing, which is what we're going to be using for, but it's used for a lot of other things. And then from sklearn dot model underscore selection, from that we want to import train, test, split. So these are is what we need for the next following few lines of code. Okay, just check on time here. Okay, yeah. I think we'll be right on the mark of 4 o'clock. Okay. So now we want to split data model into X and Y. So this is going to be a main X and Y. So I'm just going to label it X. So X equals data model dot drop star type comma Y. I'm going to do np.array around it. And I just realized the comma 1, I'm totally blanking on what the comma 1 means. So please excuse me for that, but just follow along as I do it. Okay, and Y equals data model brackets start. Okay, now this should make a lot of sense since we are basically doing the same thing as what we did before, but instead of with data predict, we're doing it with data model. Okay, so now with this X and Y, now that we've separated it, we have to split it up even more. It has to be, there's something called training sets and testing sets. So we want to train our data on X and Y, a certain portion of it, and we want to test it on X and Y so that we can evaluate how well it was able to learn. So we can do this simple function, xtrain, and then xtest, comma, ytrain, comma, ytest equals sklearn dot model selection. Or actually, no, we can just do train test split since we already imported that. And we can put x, the 3 arguments are x, y, and test size, test underscore size equals 0.2. Okay, I hope everyone's able to get that coded down. And I'll just explain what that means. So first we'll talk about the right side of this. Train test split is the function. It basically splits 2 variables, x and y, into xtrain, xtest, ytrain, and ytest. And it reserves 20% of both x and y for testing purposes only. And that's what test size equals 0.2 means. So 80% of the data is being used to train the model, and 20% of it is being used to test the model, which is a pretty good distribution, split. But you can try 80-20, you can try 75-25, you can try 50-50. For this case, you can 80-20 seem to be the best in terms of results. So you can always test it on your data. Some models might do better with less training data. Some models probably will do better with more training data, but you don't want to give it like 99% training data. So you should always have a good balance. Okay, just checking the chat here. Okay, looks like everyone's good. Yeah, please mention if you want me to slow down. I'll be happy to slow down and explain things. Okay. Okay, next what we're talking about is something that I found out in my case. I don't know if it's for the data, but I needed to convert my data into tensor, which is a simple function called tf.convert to tensor. So let me paste the code in the chat, and you can copy and paste it into Colab and it's pretty self-explanatory. It converts xtrain, xtest, ytrain, ytest to tensor. So go ahead and do that just by pasting it into another block like this. Oh, I forgot to run the previous block of code. That's why it's showing an error. So let me go ahead. It should now produce an error. Okay, good. Was everybody able to do that? Okay. So Sanjeev, a tensor, from what I was able to learn, a tensor is just an easier format for the model to look at. So obviously it comes from TensorFlow. So in this case, we're doing two categorical and then convert that to tensor. So it's just an easier format for the model to read. Okay. So now we can actually go into the model creation. So now we can go to actually coding a model. Okay. So firstly, we have to import some stuff for the model. So import Keras, which is our model, the library which we're going to use to create our model. And from keras.models, we're going to import the sequential model. Okay, and hopefully the autocorrect features will save you some time in Colab. From keras.layers, we want to import dense. And I'll explain what each of these means once we actually code it. Okay. And now the following code, we want to put it into a function. I'm calling mine classification model. Now we can easily call it later. That's basically what we're doing. We're creating the model, and then in the next block, we're going to call it. Okay, so in the function, we're going to do model equals sequential. Okay, so we're going to instantiate our model by doing sequential. Okay, so what does sequential mean? Sequential basically means we initialize the model and make it a sequence of layers. Okay, that's basically what sequential means. Okay. So in the next three lines, we're going to do model.add. Now here's where we add our layers, the input, hidden layers, and the output. So we're going to add a dense layer. And in that dense layer, we're going to pass in the number of total columns we have, which is 7. And now we're going to do an activation equals RELU. Okay, and I'll explain what activation means after we finish all the arguments. And then we put input, shape, and then equals, that parentheses, 6, and then a comma. Okay. And the reason why we don't put anything after the comma is because it basically knows that it just counts all the columns. If you put a comma and then nothing, it just it knows that it knows to get all the rows. And 6 because the input is 6 columns. Okay, so now let me explain what dense means. So in this case, a dense is nothing but the input layer. And yeah. And okay, so the activation function is the second argument. And so this activation function is where the weights and biases go after they have been calculated or tweaked. Okay, so this is where the weights and biases are located. The activation function's purpose is to make sense of all these inputs, weights, and biases in a linear or non-linear fashion. So ReLU, it means rectify linear unit. Okay, so it basically finds a linear way to make sense of the data. So for input, ReLU is basically what you use most of the time, but we're going to be using a different activation function for the output, since the output is not necessarily linear it's not linear. And so for the second layer, we're going to be adding another dense layer, and this is for a hidden function. So for this, we're going to have 128 nodes inside this dense layer. So the purpose of making this 128 nodes is to basically increase the complexity of the data and allow the data to make more complex relationships between the input and the output. So with more nodes, there are more weights and biases, and with more weights and biases, it can more intelligently learn the data. So 128, you can experiment with 64, 128, 256. As you go higher, obviously, it's more computationally intensive. So I would try to stay for classification. You can do 64, 128, maybe 256, but I would not go beyond 256 unless it's a really complex problem. Okay, so that's the first argument. The second argument is activation. And for this, we're going to also do Rayleigh. Okay, so that's our hidden layer taken care of. And now this is our output layer, which is another dense layer. All these are dense layers. Okay, so our output layer, first we have to define how many nodes it has. So the output can be one of 6 choices. So we put 6, which corresponds to the 6 star types. And our activation function for this is going to be softmax. Formatting here. Okay, softmax. So softmax is, it basically spits out a percentage for which it thinks the answer should be in. So in this case, there are 6 options for star types, 0, 1, 2, 3, 4, 5. And the model would output in percentages how confident it feels with each answer. Okay, so let's say if it was like a cat or dog classification problem, the softmax would assign a percentage to each element and say how confident it is that element. So let's say it thought 75% confidence that it was a dog and 25% confidence it was a cat. So the model is basically trying to say that it thinks it's a dog over a cat. Okay, so going back to this example, there are 6 possible answer choices, and the model will assign a probability to each, and we'll just extract the maximum percentage which we see, and then call that the prediction. Okay. So now we do model.compile. Now we compile everything. Now that we've added all the layers, now we compile it. So the first argument is optimizer, and this there are multiple optimizers out there. They're mostly arbitrarily chosen. I've chosen Atom because it's one of the most popular optimizers. They can get pretty technical in nature. So yeah, the most common one is Atom. I couldn't go into a lot of depth about optimizers, but please, I do apologize for not going in depth with it. So the optimizer is Atom, pretty commonly chosen. And next, we're going to do something called the loss function, which I'll explain after. I type categorical, cross, entropy. Okay, so what a loss function does, it keeps track of how inaccurate the model is. So we can easily keep track of accuracy, but we wanted to also keep track of how inaccurate it is, so that it can make a function out of it and then put it back into the model, and so it can learn from its mistakes and thus tweak its weights and biases accordingly. Okay. And finally, we provide a argument called metrics, and in this we put brackets and then accuracy, and we basically wanted to show the accuracy as it's going along. Okay, and finally, in the last thing, we have to do return model. It returns our model. Okay. Okay, In terms of time, we're running a little bit short, so I will speed up a little bit. So we get to cover the final part, which is being able to call the method, fit, evaluate, and predict using the model. Okay, so in this, we're going to do model equals classification model, which is basically, we're just calling the method that we just defined and putting it in the model. Okay, and then we're going to fit the model. And this is pretty self-explanatory, .fit. Like I said, we're going to train it with xtrain, ytrain, and then we're going to provide it test data, also called validation data. We're going to make that equal to x test, y test. Okay, so those are the two things it's going to check on to see how it's doing. Okay, and then we're going to do something called epochs. So epochs, if I were to put it simply, is how many passes it does throughout the whole data set. So it can go through the data once, but that can only provide so much accuracy. So it goes through the data again and tries to test its knowledge again so that it can better learn the data. It's basically saying how many times the model fitting is run. Okay, and each time it runs, it remembers its weights and biases and what it got right and what it got wrong, so that it can continue tweaking those so it can correctly identify the relationship between the input and the output. Okay, so this is how epochs work. Okay, since I haven't been running the program, to run the whole program until the point where we got into, you can just click this run time, and then you can say run before. And it basically runs all the cells before the current cell. Okay. Okay, now we do evaluate the model. We can do scores equals, this is where we store all the scores, model.evaluate, and we put in x test, y test. Okay. This is just for us to see, to evaluate how the model did. Okay, and then this next part, we're going to print out its accuracy. So I think it'll be easier if I just put it in the chat, because it's a lot of it's a bit of formatting to get the accuracy. So if you wouldn't mind pasting that into your Colab, it basically prints out the accuracy in percentage, and then error in the next line, and then using the scores variable. Okay. So this basically shows how well the model did. Okay, so let me run this. And you can see epoch, it goes through it 50 times. So there are 50 epochs. And each time, let me just scroll to the top, the first epoch, you can see its accuracy was 35%. And the next accuracy was 36. And as you go down, you can see it has improved to 50% by the time it reaches epoch number 10. And by the time it reaches epoch 50, it has achieved 96%. So its accuracy was good overall. Let me just see if I can run it again and try to get a better accuracy. Okay, this time was really good, 98% accuracy, and the final accuracy it got on the testing data set was 95%. So it did a pretty good job, really good job of identifying stars based on their characteristics. Okay, so that was a pretty good a way of coding a model and getting it to predict using our test data. So the model is looking good with data it was fed, but now let's give it some data it has never actually seen before. So if you remember, we allocated 90% of the data for training and testing, and the other 10% for prediction. Well, this is what we're going to do now, the prediction. So if you would bear with me for another few minutes, I know it's already past 4, but if you would hang around with me for a few more minutes, we can go through quickly how to actually test the data for a final time. So this is going to be an important line which we're going to put into the program. Let me just put it in the chat. And it basically put all the stars in one array. Okay, so that we can easily remember, since we replaced data with numbers, the star type is 0, 1, 2, 3, 4, 5, 6, right? So we want to map that to a specific star. So we put it into an array and then call that index on it. So result 0 is nothing but brown dwarf. So that's how we output the star we're going to actually predict. So let me just paste it in here. And now what we do is we get actually predict the data. So predicted equals model.predict. We put data predict x, which is what we used, what we did a long time ago to separate the data. Okay, so it stores all its predicted values in predicted. So now we have to loop through this, to parse this predicted variable. So for I in range, then predict data predict y. You can also do, for instead of putting data predict y, you can put predicted, or you can put data predict x, all of which hold the same number of values. Okay, and in this for loop, we are going to print the actual value, comma, which is result data predict y I, with the index of I. So let me explain what goes on here exactly. So we look at the data predict y, which is where actual answer is, and we then, since that prints out a number between 0 and 6, we want to then index it using the results variable, and so it'll print out brown dwarf, red dwarf, all the other types of stars. So that's the actual star. And then now we print out what the model actually predicted. So now we do predicted, comma, result. We can reference it, and then now here's something different that I did. Let me just type it down, and then I can explain it. That seems about right. And then of course we can do a new line after that. Okay, so what this does is predicted I goes through our predictions, and then so each index holds 6 values. So it holds an array of 6 elements, and it assigns a 0 or a 1 to that based on its prediction. So if the first index is 0, that means it's not a brown dwarf. If the second index is 0, that means it's not a red dwarf. But if the third index is a 1, that means it's a white dwarf. So we just want to pick out the maximum of those and see which index is it located in. So we do np.argmax predicted I, and then we put result brackets around it so that we can print out whether it's a brown, red, or white dwarf. Okay, I think it'd be easier if I paste this in the chat, since that was a pretty complex thing that I just said. So yeah, you can put that in there. Okay. So, and that will basically show the actual versus the predicted. Okay, and then if you run this, oh yeah, I forgot the colon right there. So make sure you put the colon there. Okay, so now it prints the actual answer and then what it predicted. So brown dwarf, so that it got it correct. All these were correct. Let's try to find one where it purposely got it wrong. Not purposely, but it got it wrong. Let's see. Okay, the last one. So the actual answer was a hypergiant, but it predicted it to be a supergiant. Okay. So if you were to look at this, there's probably a pretty good reason for this. And I know this because I know the different types of stars and how close they are to each other. So if we go back to the PowerPoint and we go to the part which talks about the distribution of stars, we can see that supergiants and hypergiants are really similar to each other in terms of their characteristics, like luminosity, spectral class, and stuff like that. So understandably, the model thought the characteristics of this supergiant were closer to its definition of a hypergiant. So it thought this hypergiant was actually a supergiant. So the model was basically not trained enough to know that, to distinguish between a really good supergiant versus like a really similar supergiant, but it's actually a hypergiant. So this just shows the importance of training your data. So since the model was only trained on 240 stars, and even less than that because we distributed 90% of it, only 90% of it, it knows only so much from this data. So it just doesn't have knowledge to classify a star that has characteristics of two different types, like supergiant and hypergiant in this case. That's why it's so important to test your data test your model on data it has never seen before, so it can reveal any shortcomings that might not be obvious from the training and testing. So 95% looked good in theory, but it's actually proving to be, the more you test on it, the more you realize it inaccurately predicts like 1 out of every 20 or 1 out of every 30 stars. So that's just important to know. And this doesn't mean that model should be 100% accuracy all the time. It just means that you shouldn't. It just has to be usable in the real world. Okay, any fundamental flaw should be monitored and fixed, but don't let it stop you from coding a model. Okay, so I hope you guys were able to get something out of this. And just so you know, if there's anything I want you to take away from this, it's to know that there's always a project for everyone. And don't forget that you can have a contribution to society through your skills and ideas. My example is astronomy related, but you can pursue projects from like cancer, predicting cancer, to like making robots with AI. There are just so many domains and unexplored ideas. And the first time, obviously, like from personal experience, I know that I struggled for hours and hours trying, and all I ended up with was obsolete code. But if you persevere through the many ideas that are listed here in this chart, it's inevitable that you'll find one which you really enjoy. Okay. And I just remember this quick quote. You should do computer science not because it's easy, but because it's hard. Okay. So that concludes our workshop. I hope I didn't bore you too much. That's all from me. And before you leave, I would like to send the link to this Colab so that you can look at this code even further if you would like to. So here's the link to the Colab, the fully coded one with comments and annotations. So I hope it'll help you for your future projects. I really wish you guys best of luck in Hack AI. Keep hacking, and I'll hopefully see you guys in the closing ceremony. See you guys. You guys are good to go. Thanks for coming.